Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to continue our series on net ionic equations, specifically talking about acid-base net ionic equations. Now, before we start, we got to kind of review a little bit about acids and bases. Number one, for acids, they're things that donate protons. Now, in the context of acids and bases, what do we mean by the donation of a proton? We're specifically talking about the hydrogen positive one ion. Because if we calculate the protons, electrons, and neutrons of a hydrogen positive one ion, the only thing that's present is a proton. So when we use this term in acids and bases about donating a proton, we're specifically talking about the hydrogen positive one ion. So all our acids, they're going to begin with H, okay? And I have a list of strong acids over here that all begin with H, okay? Now, there are other acids that begin with H, but they're not strong. So if it's not on this list and it begins with H, it's a weak acid. So we have some acids that are strong and we have some acids that are weak. And this becomes really, really important to define the difference between those two when doing net ionic equations. So I make my students memorize these 7 strong acids. Same thing is going to be true for the bases, okay? Bases are going to be things that are going to accept these protons, okay? And usually it's a negative ion, because if hydrogen's a positive ion, okay, well, the things that accept the protons probably should be negative, because positive and negatives attract each other, okay? Now, hydroxide's probably the most common ion that we have that's a base. And if you look at all these strong bases, every single one of them ends with hydroxide. But there are other bases that are negative ions, like sulfide ions can act like a base. Carbonate ions can act like a base too, because they can accept that proton. They just wouldn't be in this classification of being a strong base. Only these 8 are considered strong bases. Anything off of that list, okay, would not be considered a strong base, and therefore would be qualified more as a weak base if it indeed will accept a proton. Last thing too, we need to know our naming. We need to know how things change from like basic normal naming to acid naming, meaning like if you have something that ends in IDE, like HCl, some people might want to call that hydrogen chloride. As an acid, we would call that hydrochloric acid, okay? And so just over here, you know, this is perchloric acid, this is chloric acid, this is sulfuric acid, and this is nitric acid. So if you forget about the naming of acids, I encourage you to watch the video. It's called Formula Writing Level 4, and that will talk about the naming of acids, okay? But today's lesson's all about kind of doing net ionic equations, and so I'm going to erase kind of these notes about acids and bases. I'm going to leave this side up over here because this is, you know, some stuff that we're going to kind of refer to for the rest of the lesson. So let me erase these notes right here that we just wrote down. And what we're going to be doing today is we're going to take a look at several examples of some balanced chemical equations, and then we're going to try to turn them into complete ionic equations, and then ultimately to net ionic equations, because most professors or instructors or College Board on the AP test, if you're an AP student, they want this answer to be a net ionic equation. So let's start with our first example. It's the most common acid-base reaction that instructors tend to use, and that's hydrochloric acid with sodium hydroxide. So the first thing that we got to be able to do is to write just our balanced chemical equation, okay? Hydroxide, being one of the most common bases that accepts proton, is checking out that proton. It says hydroxide's basically saying, hey, proton, why don't we hook up, okay, and form some water? Because when the H is donated to the hydroxide, which is a base, so remember, the acid's donating the proton, the hydroxide's accepting the proton, it's going to end up forming water. We typically won't call this HOH. We'll say it's H2O. And H2O is a molecular compound. And I want to remind you, in a net ionic equation, that's something that we keep together. So I'm just going to list this as a liquid to remind us, hey, that's a molecular compound. We're going to keep that guy together, okay? Well, if the proton is donated to the hydroxide to form water, that's going to leave sodium to hook up with the chlorine. And here's our balanced chemical equation, okay? Now, from the balanced chemical equation, we got to turn it into a complete ionic equation. And this is the hardest part, okay? This is where you have to go through each of the compounds. I lost my 2 there. You got to go through each of these compounds and determine, do I split it up, okay, or do I keep it together? And here are some of the rules that we talked about in the previous video. A reminder, we have some ionic compounds that split up and some that we keep together. If it's soluble, you split it up. If you keep it together, okay, that means it's an insoluble. Our strong acids and bases, things that are on this list, we're going to split up, okay? But if they're a weak acid or a base, we're going to keep it together, okay? So this is the strong bases that we'd split up, okay? If it's not on this list, we would keep it together. And then, of course, molecular compounds like the water we just formed, we're going to keep that together as well. Okay, so let's kind of go through here. HCl, is it on the list? It is. It's right here. We're splitting it up. Sodium hydroxide, that's a base. Is it on the list? It is. It's right here. We're splitting it up. So the hydrochloric acid in solution will never be hydrochloric acid as like a compound put together. It is always just a bunch of ions floating around, both protons and chloride ions. Same is true for the sodium hydroxide. When it's in water, okay, you're never going to see sodium hydroxide together. It's just sodium ions and hydroxide ions. Now, this hydroxide ion is saying, hey, proton, I think you're cute. Why don't we hook up and form some water? And we made a molecular compound, and that molecular compound of water is going to stay together, okay? Now, I look at sodium chloride. This is an ionic compound. According to our solubility rules, an alkali metal is always soluble, and ionic compounds that are soluble, we're going to split up. And this is the hardest part of the net ionic equation, is going from this step to this step, okay? Because going from this step to this step is super easy. All you have to do is cross out the spectator ions. And those are things that are the same thing on both sides. In this case, the sodium, it's just watching the chemical reaction take place. It's not involved in it. It's just present and it's watching it. We call these things spectator ions. Same thing for the chloride. The chloride ions are just watching the chemical reaction occur between the proton and the hydroxide ion. So the proton in water, it's a solution, is going to run into a hydroxide in solution, and it's going to form water, and that's a molecular compound, so we leave it together. So this is your net ionic equation for the classic hydrochloric acid sodium hydroxide equation. Okay, well, let's kind of mix it up because we dealt with 2 things that are strong, okay? We've got a strong acid with a strong base. What happens if one of them was weak, okay? How would that change our net ionic equation? Okay, well, let's kind of put something in here that's weak. Let's say we do hydrofluoric acid with sodium hydroxide, okay? So the sodium hydroxide is the same thing in the last problem. I want to remind you that that is a strong base, so I know I'm going to split this guy up. Let's take a look at hydrofluoric acid, okay? We come over here to our strong acids, and I don't see hydrofluoric acid on this list. If it's not on this list, that means that this is a weak acid, okay? So that's going to be something that we don't split up when we come down here to do the complete ionic equation. That's how this problem is different than the previous problem. As far as the chemical reaction that occurs, though, this hydroxide is still saying, hey, proton, I think you're kind of cute. Why don't we hook up and form some water? Okay, and it's going to make the same molecular compound, water, that we're going to keep together because we keep together molecular compounds, and that's going to leave the sodium to hook up with the fluoride. So as far as a reaction, it kind of looks the same as the balanced chemical equation. But like I said, when we come down to the complete ionic equation, because this is weak, we're going to keep it together, okay? Because it's a weak acid. We're still going to split up our strong base, The water is still going to stay together because it's a molecular compound. And this is an ionic compound. It has an alkali metal in it, which means it's soluble, and that means we're going to split it up. And then we're going to cancel out the spectator ion. In this case, the only spectator ion is going to be the sodium. Okay, so our net ionic equation looks like this. We got some hydrofluoric acid that's together, and the hydroxide comes in as an ion and says, hey, proton, I think you're kind of cute. Why don't we form some water? And that's going to bump out the fluoride, and the fluoride is just going to be by itself, okay, in solution. Okay, so this is how a weak acid with a strong base net ionic equation looks different than the previous problem, which was a strong acid with a strong base. Okay, this is a weak acid with a strong base. Okay, all right, let's move on to some other bases that are not hydroxide. Let's say I have a hydrochloric acid with sodium sulfide. Okay, and we're going to take a look at this balanced chemical equation. Okay, so the sulfide ion here is actually acting like a base. It likes to accept the proton. So the sulfide saying, hey, proton, I think you're kind of cute. But instead of forming H2O, there's no O here, it's S. So it's going to form H2S. And H2S is also a molecular compound, and it's a gas. Okay, a lot of times this is the additive that they add to methane or propane to give you that rotten egg smell so that you know that you have a leak. So this is kind of a molecular compound that I make my students memorize. I have it down here with other molecular compounds like water, carbon dioxide, and H2S tends to be the new one that they have to remember as it being a molecular compound. But if the sulfide grabs the proton, that means that the sodium and the chlorine are going to hook up. And if I was going to do a balanced chemical equation, 2 sodiums, so I have 2 sodiums, but that gives me 2 chlorines. So now I have 2 chlorines, but that gives me 2 protons, but I already have 2 H's, so I think this is a balanced chemical equation. And now we got to decide what splits up and what stays together. Okay, strong acid, we're going to split it up, and it's going to make 2 protons and 2 chloride ions. 2 protons and 2 chloride ions. Alkali metals are always soluble in water, so we're going to split this up. It's going to make 2 sodium ions and 1 sulfide ion. That's a -2. Okay, and basically the sulfide saying, hey, protons, why don't we form some H2S gas? Alkali metal, so it's going to be soluble, so it's going to make 2 sodium ions and 2 chloride ions. And that's the hard part, is just going through each of these compounds and saying, do we keep it together or do we split it up, kind of according to these rules that we have on the board. Okay, so the things that are spectators, okay, are going to be the chloride ions and the sodium ions, and whatever's remaining is going to be your net ionic equation. So in this problem, we have 2 protons. They're going to be accepted by the sulfide ion, and it's going to form some H2S gas. This is our net ionic equation, and I make my students write down states of matter, okay, and don't forget your charges as well, because that's the important piece of net ionic equation. So this is a strong acid with a base that's not a hydroxide. In this case, it's a sulfide, okay, because remember, from our notes before, sulfides can be bases. And then the last one that we're going to talk about today is a carbonate with an acid. So let's kind of do a carbonate. And carbonates and bicarbonates are going to kind of act in the same notion. It just matters how many protons they're going to pick up. Okay. So in this problem, we're going to take a look at hydrochloric acid with potassium carbonate. So it's going to look something like this, okay? And the carbonate is going to do the same thing. If it's a base, it's going to pick up the proton, okay? Now remember, carbonate is a -2, so it's going to need 2 protons, okay, in order to balance out that chemical equation, and that's going to leave the potassium with the chloride. And if we go ahead and try to balance this, we got 2 potassiums, so we got 2 potassiums, that's going to give me 2 chlorines, so that's going to give me 2 chlorines. It's also going to give me 2 hydrogens, but I already have 2 hydrogens, so I have a balanced chemical equation here. And the big piece of this, okay, is understanding that when the carbonate picks up the proton and it forms this chemical carbonic acid, there's a piece of information that you need to know in chemistry. And that is when you have carbonic acid formed, okay, it's going to decompose into 2 molecular compounds that are really stable, okay? It's going to end up making water and carbon dioxide. So if you add up the hydrogens, here's the 2 hydrogens, here's the carbon, and here's the 3 oxygens, okay? So this is a piece of information that a lot of students tend to forget when doing net ionic equations, and it's just one of those things, as many other things, that you have to have kind of like memorized in chemistry, okay? So now let's decide what type of things do we split up and keep together. Strong acid, we're going to split up. Alkali metal and ionic compound splits up. It's going to split up into 2 potassium ions and 1 carbonate ion. It's going to make some molecular compounds of water and carbon dioxide because the carbonic acid is going to decompose. So the water is a liquid and the carbon dioxide is going to be a gas, okay? And it's also going to form this ionic compound that has an alkali metal in it. So we're going to split it up. And like I said, that's going to be the hardest part of this net ionic equation, is going from here to here, because after that, you just got to cancel out the spectators, which are going to be the potassium ions and the chloride ions. Anything that's left over is going to be your net ionic equation. So we're going to end up getting 2 protons in solution that are going to be attached to a carbonate ion that's in solution, and it initially makes carbonic acid, but that immediately decomposes into our 2 molecular compounds of water and carbon dioxide. So we went through a lot of different types of acid-base chemical reactions and turned them into net ionic equations. We dealt with strong acids with strong bases, weak acids with strong bases. We changed the base to sulfides and carbonates. And if you found this information helpful, please give it a like and subscribe. Even add a comment will help get the YouTube algorithm push this out to other students that might be interested in learning more about net ionic equations, okay, specifically acid-base net ionic equations.